We start this lecture with an overview, a plan for what will be presented. This pre-lecture is devoted to the introduction of a single force, friction. Now, frictional forces are omnipresent in our world. Indeed, pretty much all science prior to Galileo focused on what was directly observed, much of that being dominated by friction. Galileo, in his description of free fall, and Newton, in his first law, took as fundamental the more idealized description of motions in the absence of friction. The effects of friction then can be added back in. We will learn today exactly how to account for these effects of friction within Newton's framework. In particular, we will adopt a simple model for frictional forces that is specified by two constants for each pair of surfaces that are in contact with each other. These constants are the coefficients of static and kinetic friction. We will then address specific examples to demonstrate how we can use these constants to account for frictional forces within Newton's framework. Last time we introduced several new forces. The gravitational force is a fundamental force of nature that exists between any two objects of any size that have mass. Today, we will introduce a force, friction, that is more similar to the contact forces we discussed last time. In general, the force between two surfaces that are in contact has components both perpendicular and parallel to the surfaces. The perpendicular component is the normal force we discussed last time. The parallel component is called the friction force. The direction of the friction force is always such that it opposes any relative motion of the two surfaces. We distinguish between two kinds of friction forces. Kinetic friction refers to cases in which one surface moves relative to the other, such as when a box slides across the floor, while static friction refers to cases in which the surfaces do not move relative to each other, such as when a person is pushing on a stationary heavy box. The microscopic origins of these friction forces are complicated. They arise from the interactions of atoms on the surface of materials. We will not try to understand these interactions in this course. We will only be concerned with characterizing the friction forces on macroscopic objects using a simple model. When one object slides across another, the frictional force between them is found to depend linearly on the perpendicular force between them. In other words, the frictional force is proportional to the normal force. The constant of proportionality, mu sub k, is called the coefficient of kinetic friction. This constant depends only on the properties of the two surfaces and not on the size or weight of the objects. We'll now do an example to see how this works. Suppose a box is given an initial shove, after which it slides on a horizontal floor. If the coefficient of kinetic friction between the floor and the box is mu sub k, what is the acceleration of the box as it slows to a stop? We will follow the problem-solving procedure we developed last time. We first draw the free body diagram for the box. The forces acting on the box once it is in motion are the weight of the box, the normal force exerted by the ground on the box, and the kinetic friction force. We'll now choose the direction of x and y axes as shown and write down Newton's second law for both the x and y directions. The acceleration in the y direction is 0. Therefore, the magnitude of the normal force is just equal to the weight of the box. Turning now to the x direction, we see that we can determine the acceleration since we know the magnitude of the kinetic friction force. Namely, the acceleration in the x direction is just equal to the coefficient of kinetic friction times little g. The minus sign indicates that the direction of the acceleration is to the left. Note that the acceleration does not depend upon the mass of the box. We see that the box slows down with a constant acceleration whose magnitude depends only on the coefficient of kinetic friction. We'll now turn to another everyday example that illustrates how we account for static friction. Suppose a box is at rest on a horizontal floor and we pull gently on a rope attached to it. The box does not move. Pull a bit harder and the box still does not move. If we keep pulling harder and harder, eventually the box does move. How do we describe what happened in terms of Newton's laws? Well, clearly the acceleration of the box was 0 until it began to move. We know then from Newton's second law that until the box began to move, the total force on the box was 0. Since the rope was exerting a force on the box, directed to the right, there must have been another force of the same magnitude that was directed to the left. This force is the static friction force, F. It opposes the horizontal motion that the tension force would have produced. The magnitude of the tension force reflects how hard we pull. The harder we pull, the bigger the tension gets, and therefore, the bigger the frictional force becomes. This dependence of the frictional force on the tension is demonstrated in the plot. There is a limit to the force that friction can provide, though, and eventually we are able to move the box just by pulling harder. This maximum value of the force that static friction can provide is once again just proportional to the normal force. In this case, the constant of proportionality is called the coefficient of static friction, mu sub s, and depends only on the properties of the two surfaces. This behavior of the static friction force that we have described is captured in an inequality, namely that the static friction force is less than or equal to the coefficient of static friction times the normal force. Note the important difference here between kinetic and static friction. The kinetic force is always equal to mu sub k times n, while the static force is not always equal to mu sub s times n. In fact, the static force is only equal to mu sub s times n just before the surfaces begin to move. In all other cases, the static force is less than this maximum force. Just as it was for the normal force and for the tension force, the magnitude of the static frictional force must be determined from Newton's second law. The static frictional force is simply what it has to be to do what it does. We can summarize what we have learned about friction so far by completing the plot we have created for static friction. As we increase t beyond the point at which the box begins to move, we see that the friction force stays constant as t increases. The discontinuity at the point at which the box begins to move indicates that mu sub s is greater than mu. We will now do some examples that illustrate the use of these frictional forces within the framework of Newton's laws. Here we see a box sliding down a ramp that makes an angle theta with the horizontal. We want to calculate the acceleration of the box down the ramp. We start by drawing a picture and labeling all of the forces acting on the box. In the absence of friction between the ramp and the box, there are two forces acting on the box. Its weight, mg, which points downward, and the normal force, n, that the ramp exerts on the box. The direction of this force is perpendicular to the ramp. Right away, we can see that there is a net force directed down the plane, which gives rise to the acceleration down the plane. If there is friction between the box and the ramp, there will be an additional force that opposes this motion. Therefore, this frictional force is directed up the plane and has a magnitude equal to mu sub k times n when the box is sliding. We now need to choose a coordinate system. As we mentioned last time, choosing one axis to be parallel to the acceleration often simplifies the calculation. Therefore, we will choose our x-axis to point down the ramp and the y-axis to be perpendicular to the ramp. Finally, we write down Newton's second law for both the x and y directions. To write down the y equation, we need to find the y component of the weight. Since the normal force is perpendicular to the ramp and the weight is perpendicular to the horizontal, we see that the angle between these two forces must also be equal to theta, the angle the ramp makes with the horizontal. Therefore, we can use trigonometry to determine that the y component of the weight is just equal to the weight times the cosine of theta. Writing down Newton's second law for the y direction, we obtain the magnitude of the normal force. This result holds for both the friction and frictionless cases. We can now obtain a value for the magnitude of the frictional force from our result for the magnitude of the normal force. The x component of the weight is equal to mg sine theta. We can now write down Newton's second law in the x direction in terms of this frictional force and the component of the weight down the ramp, and then solve for the acceleration. We obtain the result that the acceleration is equal to little g times the factor sine theta minus mu sub k times the cosine of theta. We can remove the frictional force by setting mu sub k equal to 0, resulting in an acceleration equal to g sine theta. We've just determined the acceleration of a block sliding down a ramp. In particular, we see that the acceleration decreases as the angle theta decreases. If we make the angle small enough, the frictional force on the box will prevent it from accelerating at all. At such an angle, what is the magnitude of the frictional force? To answer this question, we start with the free body diagram, and we see that this diagram is identical to that from the last slide as long as we just call the frictional force F. Since the box is not moving, we have a case of static friction. The magnitude of the static friction force must be determined from Newton's second law. In particular, the magnitude of the static force must be equal to the component of the weight down the plane. As we increase theta, both the friction force and the x component of the weight increase. At some angle, theta max, the static friction force can increase no more, and the block will begin to slide. We can determine theta max by setting the static friction force equal to its maximum value, which is mu sub s times n. When we do this, we see that the tangent of theta max is just equal to the coefficient of static friction. We'll close this pre-lecture by doing one more example involving friction, that of a car of mass m rounding a circular turn of radius r. If the coefficient of static friction between the tires on the road is mu sub s, how fast can the car go around the turn without skidding off the road? Well, perhaps your first question here is, why in the world are we giving you the static coefficient of friction when the car is clearly moving? Well, the answer is that the tires are rolling. The surfaces of the tires are not sliding relative to the surface of the road. If they were, the car would already be skidding. During normal driving, it is the static friction between the tires and the road that makes a car speed up, slow down, and turn corners. We start, as always, by drawing a free body diagram for the car. From this diagram, we see it is just the frictional force F that is responsible for the centripetal acceleration of the car. Next, we choose the x-axis to point toward the center of the circle to align it with the direction of the acceleration. We choose the y-axis to be vertically up. Writing Newton's second law for the y direction, we see that the magnitude of the normal force is just equal to the weight of the car. Writing Newton's second law for the x direction, we see that the frictional force must be equal to the mass of the car times the centripetal acceleration. Now we know the centripetal acceleration is equal to the square of the speed divided by the radius of the turn. Therefore, as the car's speed increases, the frictional force must also increase. There is a limit, though, as to how much this frictional force can increase. This limit is determined by the coefficient of static friction, mu sub s. This maximum frictional force, then, produces the maximum centripetal acceleration, which determines the maximum velocity. Therefore, we obtain the maximum speed that the car can make the turn without skidding is proportional to the square root of the product of the turning radius and the coefficient of static friction. This result makes sense. The car's maximum speed should increase if either the friction increases or the turning radius increases. We conclude with a brief discussion of the main points of this pre-lecture. First, the contact force between two surfaces can have two components: the normal force, which is perpendicular to the surfaces, and the frictional force, which is parallel to the surfaces. Second, we adopted a simple model of the kinetic friction forces that exist between surfaces in relative motion in terms of a single quantity, the coefficient of kinetic friction, which can be determined empirically for any pair of surfaces. In particular, we assume the magnitude of the kinetic frictional force is always equal to the product of this coefficient and the normal force each surface exerts on the other. The direction of the kinetic friction force always opposes the relative motion. Third, we adopted a simple model of the static friction forces that exist between surfaces that are not in relative motion, in terms of another quantity, the coefficient of static friction, which can also be determined empirically for any pair of surfaces. The main difference here is that the magnitude of the static frictional force is related to the normal force between the surfaces by an inequality rather than an equality. That is, we say that the magnitude of the static frictional force is less than or equal to the product of the coefficient of static friction and the normal force. This inequality reflects that in any particular case, the static friction force must be determined from Newton's second law. The static frictional force is simply what it has to be to do what it does.